Speed is the rate that distance is changing, and acceleration is the rate that speed is changing, or in one way, the speed that speed is changing. If we can write speed as distance over time, and acceleration is simply velocity over time, or the change of that. If I gave you a vehicle that could go from 0 to 30 meters a second in 2 seconds, calculating its acceleration is easy. V over t, expand your delta notation, show me the steps, you got an answer. Now at this point, a change in speed of 15 meters per second for every second this thing traveled, is that a high acceleration? Well, what I know right now is no car on planet Earth will do that. And if it did, you would be injured. By the end of this slide, you should be able to make that assessment. I want you to be able to look at the number and go, no, that's not right. And I can tell you right now that no car does this. And I want you to be able to do the same thing by the end. Let's use common sense to rearrange some of these formulas. If I pay you $15 an hour for 3 hours, what is your total you've earned? $45, right? If your car accelerates at 15 meters per second, every single second, for 3 seconds, what is your final speed? I think you go, oh, I get it. It's picking up speed at 15 meters a second, every second, for 3 seconds. I multiply. Well, how would you make a formula? All the formula is taking the specific example you have and substituting out the idea it represents. So 45 meters per second becomes speed. 3 seconds is talking about time. And acceleration is that. You are going from a specific example to very general. And why did I not have a delta V in here? Because, frankly, we like to start our problems off from rest. Let's look at my speedometer. Canadian, American, physicist. A car would traditionally be reported 0 to 60 in 4 seconds. American commercials will still do that. But in Canada, we're in metric. So 0 to 60 in 4 seconds would be saying 0 to 100 kilometers an hour in 4 seconds. That's is that booting? Getting up to highway speed in 4 seconds? Grandma will spill her tea. But in metric, it would be 27.7. The car would go, but it's the equivalent. It's how fast did this dial sweep? In proper form, this is 27.7 meters per second in 10 seconds, if that's what it took the car to do. Let's say it took it 10 seconds to get here. Then, if we rounded this, this means our car is gaining speed at 3 meters a second every single second. Get the idea? If this car could accelerate at this rate for 100 seconds, it would reach the astronomical speed of 2,770 meters per second. Well, what we want to do is get away from the speedometer and switch it to this. If the speedometer went up nice and uniformly, we'd get this lovely velocity time graph. Nice straight line. But the distance would begin to accumulate progressively faster and faster, because with each passing second, you're going quicker. Let's take a close look at this graph. This car went from 0 to 30 meters a second, which is highway speed, in 8 seconds. That's a pretty typical clip. Oddly enough, the highest accelerating production car is the Honda Civic. It can come out of the hole faster than anyone else, believe it or not. So the Honda Civic can really boot when you step on the gas pedal. It'll get up to speed very rapidly. Doesn't mean it has the highest top speed, it just means it's got guts. So this car has changed in speed 30 meters a second in 8 seconds. So its acceleration is 4 meters per second per second. To get the acceleration off the graph, you can simply take its slope. delta y over delta x is simply v over t. And you just get the slope of the speed time graph. The distance time graph has now got a problem. Previously, we could take the slope of the distance time graph and get velocity. That doesn't work here because there is no slope of the distance time graph. The slope is changing as we go. So if you get a curved distance time graph, you have to take smaller slopes at intervals along the way and recompute speed. So if we go back to this one, the slope here generated the value there. The slope up here generated this value there. Let's look at an example. This curve I did not plot mathematically, so it's not going to work out perfectly. This is just a freehand curve. What if I want the slope in between that interval? That would mean pretending the curve looked like that, which is a terrible approximation of the curve. But if you take a good look, and I slide this line over a little bit to there, this is what's called a tangent line. You can see that these two are parallel because I literally just moved this over. And the slope of this line is matching the curve right there. So if you were to take this slope as an approximation of the curve, it's a terrible approximation of the curve's slope here. It's terrible up here. But smack in between these two, this line perfectly approximates the slope of the curve. So it's averaging the slope for you. And this line is called the tangent line in math. This line is called the secant line. The tangent line requires calculus to get its value. The secant line, you can eyeball it. And it will work 100% in this course. So we call this doing stepwise slopes. You go up little step at a time, calculating the slope as you go. Here would be an example of a stepwise slope, calculating time at a certain interval. Let's say I want to know the speed between second 9 and 10. Well, I go over to second 9 and 10 on the graph, and I got two choices. Calculate the speed directly off my data table like this, or I go to the graph and I set up rise over run, and I calculate it off the graph if I don't have the data. To know the speed time graph, you simply repeat these between every pair of points. So you would need to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 slopes, and you would have 10 velocities. Now, where is that slope matching for time? It matches right in the middle. So when you calculated the speed of 19 meters a second, you would say that this vehicle passed through that speed not at 9 seconds, not at 10, but the average, right in between, 9.5 seconds. Now, where can we start getting some power here? The acceleration when you fall is 9.8 meters per second squared. This means for every second you fall, you gain roughly 10 meters of second speed. You ever heard people estimating things going, you're in the ballpark? I like to call it ballparking. If you watch my conversion video, here's a simple conversion of kilometers an hour to meters per second. Basic rule is, if you're heading to meters a second, divide by 3.6. If you want to go from meters a second to kilometers an hour, times by 3.6. So if you let me get away with rounding gravity to this, and then rounding this number to 4, very crudely, when you fall, you gain speed at 40 kilometers an hour every single second you fall. If you fall for 3 seconds using this rounding, you reach 30 meters per second. In both cases, using this number or that number, a 3-second fall puts you at higher than highway speed. And once you memorize this, just commit it to memory. Highway speed is about 30 meters a second. You can then easily tell when you get a calculation, there's no way the hummingbird went 400 meters a second because highway speed's 30. And if someone says, when that pitcher threw the ball, it accelerated at 200 meters per second. And you're like, dude, Gravity is only 10. You just reported it at more than 20 times more acceleration than if it fell. Nobody can throw a ball like that. And suddenly, you start to have intuitive power over this. I like rounding. Most teachers do not. Drives me nuts when physics teachers are having their kids use 9.806. So yeah, I'm criticizing other teachers for, too many decimal points. We're not administering, therapy drugs to someone where we got to get it within the milliliter. We're trying to learn giant trends and patterns. So I really think severely rounding is a good idea when you start. It puts you into thinking. And I'm going to show you how little the rounding makes. Gravity is 9.8. If I round it to 10, really what changes? A 3-second fall, your final speed will be a times t. There's the actual value of gravity. You get 31.4 meters per second. If we allow the Kinematics rounding to the nice, lovely number 10, you can do it in your head. It's 30 meters a second. Convert it to kilometers an hour. And we're looking at this difference between the real value you would reach and my value from rounding. It's 2%. I guarantee you our lab equipment could not detect it. If you did the acceleration due to gravity in class, and I've done it at university, and with high precision equipment, we were lucky to hit 9.6. You will not find this value unless you really set up unbelievably precise instruments. Let's look at highway speed in my rounding again. Highway speed is 27.7. If I round it to 30 meters a second and convert back, my rounding to this value generates a speed of 108 kilometers an hour. So if I told you, oh, you can drive 30 meters a second, I've actually told you to drive 108. Who's going to catch you? Everybody supposedly says the cops will let you get away with 110, right? Well, in actual fact, you could be caught. The rounding in this case is well within the ability of police radar to catch. If you go online, you'll find that police radar guns are good for plus or minus 2 kilometers an hour. So my rounding here would put you 8 kilometers over the speed limit. The radar gun would easily detect that. Police, on the other hand, if they do not have a radar gun and they've stopped you by visual conditions, he was speeding, I flagged him over, he was going at least 120. The courts put a visual estimate of your speed from a policeman on the ground as plus or minus 10 kilometers an hour. So if the cop said, hey, Kinematics was speeding, he was doing 108, the judge would say, no, 108 plus or minus 10, he's not getting ticketed. So there are techniques we can use to decide whether the rounding is valid or not. The point of rounding is it puts calculations in your head. It's great for confidence and it's great for fumbly fingers, because then you just have this little warning tone in your head going, nah, not right. Trust me, it works way better than double checking. Give me an example. You fall for 17 seconds. Could you survive the impact? Discuss it with physics. Well, then you go, let's see. Speed is a times t. Therefore, I'm going to take the acceleration due to gravity, times it by 17 seconds, get out my old calculator, and I get 166.6 meters per second. Right? That takes a little bit of time to do, right? On the other hand, if you round gravity to 10, you go, oh, that's 10 times 17, that's 170 meters a second. Let me see. Kinematics said highway speed's about 30 meters a second. So, geez, 6 times 30 is 180. Man, that's 6 times highway speed. They hit the ground at about 600 kilometers an hour. They're dead. And that's what I mean. Now you're starting to understand why a scientist in the X-Men movie can look at the controls of a dam about to burst and go, no, and run out of there. You're like, what did they see on the instruments? So now you're able to go, in a quick matter of seconds, estimate that a falling 17 seconds, you're going to hit the ground at 600 kilometers an hour. And you go, how did teachers do that calculation in their head? Didn't do the calculation in my head, it estimated. And you'll be within 2% of the actual answer. So on a multiple choice test, Do you know how much time you can buy yourself back by doing this? So if you struggle with processing those problems, I guarantee you most multiple choice tests, you can look at the question and go, estimate, 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 and fly through the things. But it does take your willing practice. Now let's look at the DT graph again as it were a book and start to comprehend things without burying ourselves in calculations. We're going to look at a data set for continuous acceleration for an object and try to connect acceleration to distance mentally. So here again is the speed time graph and its distance time counterpart. The speed between these segments I computed and plotted here. And if you pay attention now, you may realize I've made a mistake on this graph. And you go, wait a minute, Coyote plotted the speed at 8 seconds. Didn't he tell us the speed would be the average between 7 and 8? Yes, I did. So once you can start spotting mistakes a teacher has made or a book has made, you should feel really good. Because again, what's shown on screen is flying in the face of what I taught you. And you might go, hey, wait a minute. Now you might go, why did I do this? Because I was making these graphs for an entirely different purpose for physics and death. Okay? Now, I want to show you something. This object traveled 120 meters according to this. Right? You can see it right here. And I want to show you what we can do with this to predict that if we had this speed time graph. Let's say we didn't have the distance time graph. And we just remember that it's at 120 meters. We're going to look at the speed time graph here, velocity time graph. I didn't give you any directions, though. And see if it gives us enough information to know the total distance. We know that distance is v times t, but v is changing, so we can't calculate a distance from this. But remember, we know the area under this graph is distance, because it's speed times time. Now, do you guys know how to calculate the area of a triangle? I think you might. Why don't you try it in your head right now? VI, VF, delta T. What's the formula for a triangle's area? It's 1/2 base times height. So I've got the wrong graph here, illustrating it. So, sorry, I know what I meant to do. By the time I create these slides and then narrate them, I've forgotten my graphic sequence. So here's our distance time graph. And I'm going to overlay on it the speed time graph. And you see there's the actual final distance of 120 meters. The area of a triangle is 1/2 base times height. Now what's the height of this triangle? VF minus VI. And its base is delta T. So if I do half change in height times delta T, that should give me the distance traveled, the area under the curve. What's with the triple equal sign? That means equivalence. And what it means is I'm telling you it's so. I didn't calculate, that it equals D, because you might go, where did D come from? I'm telling you, we already discussed this. Area under that line is a distance. So it's by definition. So distance is going to be base times height divided by 2. Base, 8. Height, 30. Divided by 2. It's 120. Bang on. So you can actually take the area under a speed time graph and it will tell you the total distance. Just it's a triangle now, but it's still like grade 8 mathematics. Now here's the nifty part. What if I didn't have the speed time graph and you just had the distance time graph, and instead of doing little stepwise slopes, you took a grand slope from beginning to end? That's going to be a speed. But when would it have happened? When does this yellow line match the slope of this curve at 0 seconds, at 8 seconds, or somewhere else. So this slope will be the speed smack in the middle of the graph. The average slope for the journey is 15 meters a second. So if you were accelerating smoothly from 0 to 30 meters a second, when did you pass through your average speed? It was the middle, smack in the middle. So you can actually, if you have uniform acceleration, a velocity time graph like that, giving you this lovely curved distance time graph, you can estimate the middle speed by just taking this ridiculously rounded out slope and attributing that speed to the middle and go, hey, it started from rest, shoom, and you got it. It's a really simple technique to calculate your average speed and then just go, dude, if you went from 0 to 100 evenly, then you passed through your average exactly halfway through. That is not true if you didn't accelerate evenly. And this is called a half-time method, doing the whole thing. So again, I can prove it to you. If d is vt, using the average speed of 15 meters a second for 8 seconds, we get 120 meters a second. It literally allows us to say, if this car went from 0 to highway speed evenly, we could pretend it drove the average speed dead flat the whole time and it would get the same distance. And it's going to take us a little bit to see that and be convinced of it, but it's very powerful. Now, why is this true? Why would a person driving this speed time graph achieve the same finish point as the person whose speed time graph looks like this? Well, look at these areas. They're the same. It may not look like it, right? But this is a sandwich cut in half. This is a sandwich cut in half. These are both 1/2 of the area of that square. So literally, this red box and this red triangle have the exact same surface area. Just everybody thinks their sandwich is bigger when it's cut on a diagonal because it's your brain. This allows you to take this speed time graph and replace it with that one. So instead of accelerating, you just could have gone on cruise control at the middle speed for the same duration of time, and you would be at the same location. And if you grasp this, the rest is just arithmetic. This area and that area are the same. Guaranteed. Because the only difference here is W and B are the same thing. L and H are the same thing. Just the math teachers wanted different labels. Watch here. If this person went from 0 to 20 in 10 seconds, then the area under this curve is a half base times height. Gives us a 100 meters journey. What's the average speed between 0 and 20? It's 10. The area under this curve, length times width, is the average speed times time. 10 times 10. It's 100. You get the same answer. So you can change out a constant acceleration and just pretend the person drove at the midpoint speed the whole way, and you will be bang on 100% correct. So this graph here, you could just tilt it and run it horizontal and you'd have the same result. Seven seconds. Wiley Coyote fell for 7 seconds. Now we got some power. Now we can estimate. Now we can start world domination. According to the video, Wiley Coyote fell 7 seconds, and I know every small child has always thought, geez, I wonder what kind of velocity vector that coyote had when he fell down the cliff, and exactly how far of a distance did he fall in 7 seconds. Now you can do it in your head. If you round gravity to 10, this means for every one of those 7 seconds, Wiley Coyote gained 10 meters a second speed. So 10 meters a second every second for 7 seconds means he hit the ground at 70 meters a second. Highway speed's 30, right? So that's like 230 kilometers an hour he struck the ground. Now, what was his average velocity? He fell off the cliff at 0, hits the ground at 70, so his average speed was 35 meters a second. And we can pretend that that average speed was a constant speed. You saw it on the graphs. So he fell at 35 meters a second for 7 seconds. That's just a little bit over 200. Because if I multiply 7 by 30 in my head, it's 210. So 245 meter fall. Boom! That's how you break the internet. Now you know how to estimate.